morning everyone. So today we are going to discuss about this one-bit magnitude comparator. So one-bit magnitude comparator is nothing but you are going to compare two one-bit data and you are going to plot it in the K-map and you are going to draw the logic diagram. You are going to design a logic circuit diagram which is going to compare two data A and B. So in the first case you are having A and B. So first I am taking A is equal to 0 and A is equal to 1. Right? So these are the two conditions which I am taking. So for A is equal to 0, the condition 1 is B is equal to 0, condition 2 is B is equal to 1. Similarly for the condition A is equal to 1, B is equal to 0 is the first condition, B is equal to 1 is the second condition. So now I am going to compare these two bits and I am going to plot it in the table. So in the first case A is 0 and B is also 0. So A is equal to B. So A is equal to B is high. So I am putting 1 in A is equal to B and remaining two columns are low. So I am putting the remaining two columns as 0. So next A is equal to 0 and B is equal to 1, which means that A is lesser than B. So A is lesser than B is high and the remaining two columns are low. So I am putting 0 for the remaining two columns. Third point is A is equal to 1 and B is equal to 0, which means that A is greater than B. So A is greater than B is high, so I am putting it as 1 and remaining things as 0. And the last condition is A is equal to 1 and B is equal to 1, which means that A is equal to B. So I am putting A is equal to B is high and remaining two columns as 0. So this is a truth table for the one-bit magnitude comparator. Next I am going to map these values to the K-map. So the K-map, first I am considering A is lesser than B. For A is lesser than B, 0 is 0 and the box 1 is 1 and for 2 is 0 and 3 is also 0. So I am putting 0 in the remaining boxes. So I am having only one here, so I am mapping this one. So which means that A lesser than B is equal to A bar into B. So next A equal to B. For A equal to B, 0 is equal to 1 and 1 is 0 and value of 2 is 0 and the value of 3 is. So since these two numbers are in diagonal, we cannot able to map it as a single group. So I am mapping it as a separate groups. So this will become A is equal to B is equal to, for this one it is represented as A bar B bar plus, for this group it can be represented as A B. So this is in the format of A x nor of B. So I am representing it as A x nor of B. So next for A greater than B, 0 is 0 and 1 is 0 and for 2 it is 1 and for 3 it is 0. So now I am going to map this one as a single group. So A greater than B is equal to, for this one you are having A B bar. Now I am going to draw the logic diagram for this one-bit comparator. So I am having two inputs A and B. So the first case, when A is lesser than B, which is equal to A bar into B. So I am converting this A into A bar with the help of the NOT gate. So A is converted into A bar. Next, I am going to multiply it with B. So for multiplication, I am using a AND gate. So this is A lesser than B. And next, A equal to B is A x nor of B. So I am taking A from here and B from here, and I am putting a x nor gate. So this is equal to A equal to. Next, for A greater than B is A into B bar. So I am taking A. Sorry, I am taking A from here, and I am converting this B into B bar. So I am using a NOT gate to convert B into B bar. So next I am going to make it to a AND gate. So we will get a greater than. So this is about the one-bit magnitude comparator. We have compared two one-bit numbers A and B, and we are clapping it with the K-map. And finally, we have designed a circuit which is going to perform a comparison between A and B. Thank you. We'll see the remaining things in the next class.